First of all, I would like to thank the organizers for inviting me to this very interesting meeting. So I got already a lot of inspiration already on the first day. So I hope this continues for the next days. And so I would like to present work so with a couple of co-authors, as you see, including co-authors who are here in the room. So I'm very grateful to them so that they participated also in this work. And so I would like to talk about metastability and transient dynamics in neuroscience. But since the neuroscience is going to be a little bit squeezed, so to say, since I already noticed that I will be over time. And so I'm a dynamical systems person. So I'm not a neuroscientist, even though from time to time I work in neuroscience, but I'm very much inspired by dynamics in neuroscience. So to shape theories and construct theories in dynamical systems theory, so to say, which can explain mechanisms, how things work. And we try to come up with ideas, so how things can work. And so the motivation I can, in principle, cut very short because it just shows us different, and they are just chosen arbitrarily from the literature. So examples where we have metastability, or what we would like to explain as such. So where we have different patterns of neuronal activity, so which pop up in a certain sequence. And this could be either, so to say, EEG recordings with eyes closed, where we have microstates, EEG microstates, which pop up, or we have up and down states where we have some neuronal activity for a while and then there is silence, or we have patterns here of different activity. So we have here, so to say, spiking activity here, and here we have bursting activity, or we have seizure-like activity, so which is even stimulated and gets into a completely different state for a while. And so this type of dynamics, which look very, very different in terms, so to say, of the internal dynamics, we would like to describe in a kind of general framework. So we try to get, say, a common view on this type of patterns. And so this is what has been called metastability in neuroscience. Very different things come together. So for instance, the variability of different activity patterns is called metastability, or variability of regimes, so that you get to different regimes, or variability in the landscape here, synchrony patterns, which we had just the previous talk. So as a brilliant example of this, so that you have variability in the synchronization state, or you go to different states, so to say, in the brain, or there is this concept of integration and segregation, so that different parts of the brain either work together, so to say, or not. And so you have spontaneous metastability, so that there is a spontaneous hopping between different patterns, but it can also be driven, so by an external signal. And it can repeat or it cannot repeat. So you see there's a whole variety of different, say, understandings of what metastability could be. And so we try to now look for a common framework. And this common framework, so to say, is basically in our definition, and I completely discuss it now from a dynamic systems point of view, is characterized by certain properties. So we have long-lived but transient metastable regimes. So the system is in a certain dynamical regime, either, for instance, in a bursting or in a tonic firing state, or in more complicated states like synchronized or non-synchronized, cluster synchronized, completely synchronized. There are lots of different possibilities for these regimes. And so these regimes are almost invariant, so that means you dwell on this for a certain while, and then you go away. And what is the most important property is that this type of metastable regimes have to be, so to say, or have to possess a certain property, because you have to reach them at some point. So you come from here, basically. So this is attracting this regime. You stay for a while, and then you go away. So that means these attracting and these repelling tendencies have to come together. Otherwise, it's not metastable. So because metastable means that it is transient and you go away again. So that means you stay here with a high probability for a long time, but then with probability 1, you will leave at some point, even though you don't know when this point is going to be. Now, when we look at this, so we have 2 different options how to realize this thing. So on the one hand, so what is long known is that you have multi-stable systems subject to noise. What is a multi-stable system? A multi-stable system is a system where you have different regimes, dynamical regimes, coexisting, and this is subject to noise. So this is usually shown with this type of cartoon here. It's only a bistable system where you have 2 stable states in this wells, but you can think of yourself sitting in a meadow, look back to your childhood, and you play with little balls, and then all these little valleys in the meadow will be these stable regimes, and then your ball will land in one of these valleys, and then there are the unstable sets which are here in between. And then you have initial conditions, a whole set of initial conditions, which go to this valley. And so this would be the basin of attraction of this stable regime. So they can be rather simple, like here, smooth basins of attraction, so that these are lines or manifolds in state space, so in all the variables you have. Or they can be fractal, so with a very complex structure, where you only have around each of the stable regimes, you have just all initial conditions converging. But if you go a little bit away, so there's no way to predict which of those states you really reach. But the second part, which is the more interesting, by the way, is that you have saddle type regimes with these attracting and repelling directions. And these could be simple saddles like here, so that it's points. But it could be also something complex, and this is what I would like to discuss more in detail in the following. So now to give you an idea, so what is happening is best to be explained. So when we look at the bistable system, so the ball is here, the yellow one, but you see due to the noise, it's dwelling around. So you have these attracting directions because it wants to roll back into the valley, but you have also this repelling direction that the noise can you kick over the hill and then goes here and goes back to this. So this is what you get as a metastability. So when you have noise in a multi-stable system. But the escape from this valley is also something which is not really random, even though it's noise. And this is an argument you can read, so to say, in the literature, so that it's questionable. We can call this metastability because it's totally random, but this is not so. So because when you think about such a landscape, so then, of course, you go over the smallest hill. So you try to escape from a valley. This is what you would do as a hiker also. When you stand in the valley, you look around, oh, what is the lowest altitude I have to climb up? And this is what the trajectory also is doing. So there are certain paths, and these are called the most probable exit paths, so which you would go. So there are certain channels of escape which you would take. It becomes more involved when the basins of attraction are like this. And this is what we discuss also in this talk. When you have these fractal basins of attraction, then you have unstable chaotic sets which are embedded in this basin boundary, which determine how your hopping process really happens. And so the structure of these sets is then responsible for what you are really going to observe. But so there is, of course, so to say, something I have to add. metastability realized in a multi-stable system by noise happens only for certain noise strengths. If the noise is too large, then this is what's happening. So you have different attractors here. This is a mechanical system. And so you see the probability density of your dynamics has peaks always where the former attractors, now metastable states, are. And then if you increase the noise strength, so then the ones which have the smallest basins of attraction are buried under the noise. Finally, your multi-stability disappears and everything goes over into a diffusion in state space where you don't recognize any multi-stability anymore, and then it's a purely random process. So coming back to this is what we would like to explain and provide mechanisms how this can happen. So what are the mechanisms which we could have? This one we have just discussed. So multi-stability would have attractors. These are invariant. And so that means once you reach an attractor, you sit there forever. If there is noise, you don't sit there forever. So you will leave this attracting regime here. Therefore, it's almost invariant. And then you have a whole region in state space where your trajectory will dwell. So because you're not localized to this regime only, but you will always be a little bit around, but still, so to say, recognizable in which regime you are. Now, there are other mechanisms, and there is far away from being a comprehensive view here. So this is not all the mechanisms which we can think of, but so the noise we have just discussed. Here, I have a bunch of others, so which we can discuss, and this is stable heteroclinic cycles, attractor crises, attractor merging crises. There are other crises as well. Type 1 intermittency, I will explain it what it is, and chaotic saddles, to which I will pay particular attention. Now let me give you an idea so how it would look like. So for this heteroclinic cycle, so you have 3 regimes here in the corners, and your trajectory stays in one regime, hops to another one, and then hops right here again. So it's jumping here between these 3 regimes, and each of the regimes has certain properties. So this does not need to be fixed points. It can be periodic orbits. It can be something chaotic. So what we have here, so different, it could be even different patterns. So which you would see here basically in the corners. But then you have, again, attracting directions, repelling directions. So it's, again, the same property which we have already learned about. So now for the attractor merging crisis, this looks very similar to the noise-induced transition, but it's not noise. So because formerly, so to say, before the merging crisis, you have 2 different attractors. Now they start touching, and the touching is mediated by an unstable periodic orbit. And that means this unstable periodic orbit, it acts like a bridge. So when the trajectory and the system is chaotic, so that means the trajectory goes around and comes very close to this bridge once in a while. And once in a while, when it comes close to the bridge, it has the opportunity to just jump over to the other side, dwell here for a while, comes again at random, so to say, again, close to the bridge, hops to the other side, and so on. So this is an attractor merging crisis in the logistic map, just for you to see, so that 2 bands of chaotic attractors are touching each other, and it is mediated by a periodic orbit, which loses stability here in the first period doubling. So this would be this type of behavior. There are other crises of attractors, which we could see. So this is basically here in the period 3 window of the logistic map. It's a so-called interior crisis. Before you have basically a small attractor. So this is this object. Here is the mediating orbit, which is going to be the mediating orbit. And then after the crisis, you see a big attractor, but it consists in principle of the former chaotic attractor and a chaotic saddle. I will explain in a moment what it is. And these two merge. And again, this periodic orbit is the bridge between them. So that means we see here immersed excursions to this huge object. And we will see it in a simulation here. So the yellow ball is dwelling most of the time on the green stuff. But then once in a while, so now we have to wait a little while until it's happening. So there is a little excursion coming up right now, so but it's too short probably to see. But when we end up in this one, we will see it quite clearly, so that this yellow dot is leaving this green set here and is then jumping over the blue set here and then going back to the green. So now it's going to happen. So now we start getting into it. And now you would see, let's see, where are we? Yeah, here. So the yellow dot is really jumping on this purple set here before it goes back to the green. Again, we have a bridge, so this periodic orbit, which is mediating this transition. So we have other things as well. So that means we see here the next change, and we can also run this. So we have here an intermittency. So there are different types. I show only one, but the others would also work in the same way. So you have a periodic orbit here. So then you get to the green chaotic stuff, which is right here. So you dwell a while on this dynamics, and then you go back again to something so which is periodic, because now you come back to this periodic orbit and dwell in its neighborhood. So this happens also in the periodic window, while the interior crisis, which we saw previously, is here. Then the type 1 intermittency is on this side, so where we would see this type of behavior. And so finally, we have a boundary crisis, which is also a crisis of a chaotic attractor, where the chaotic attractor, so in the literature is called usually that it disappears. This is not true. So it's not disappearing because it's still existing here, but then it's of transient nature. So that means it's a saddle. And so you will leave this saddle eventually, but you still see the remnant of this chaotic dynamics. And this is again what we can see here in the video. So we are dwelling on this object for a while. So you see the yellow point jumping around here, but at some point it really escapes and gets to another solution. All these kind of mechanisms are well known in dynamical systems theory and lead to such metastable behavior. So when we look at these transitions, so we have a whole plethora of possible mechanisms how metastability can occur. So they are also characterized by the lifetime of the different structures, which is basically mostly exponential. So meaning that this looks like a random process. But so what is this transient chaos? So let me just say some words about it. So because transient chaos and chaotic saddles, which we have just seen, are not so known as chaotic attractors. Chaotic attractors, most of the people have, of course, already known about this. This is an irregular behavior, which is characterized by the property that initially neighboring initial conditions separate exponentially. And so one can quantify this mathematically with Lyapunov exponents. They have to be positive, at least the largest one. But these are saddles. And saddles means you can reach them along their stable directions, and you can leave them along their unstable directions. And so you would leave them with probability 1 if you would put lots of initial conditions on your chaotic saddle and you look how many of your trajectories pop off. So, and when does it happen? Then you would see so that there is this decay here. You have an exponential decay, and this is the so-called escape rate. And the object itself looks like this for a periodic pendulum. And the stable and unstable directions look a little bit more complicated as what you would expect, so to say. From a settled point, you know, there is a bunch of trajectories coming there and going back. In a two-dimensional system, it's just two which go there, just two which go away. But of course, in a chaotic motion, so this looks a little bit more involved. So this is the stable direction, this is the unstable direction, and the overlay of the two is the chaotic saddle. This is this yellow thing, which is plotted here once again. So chaotic saddles are quite common. So this is a very common object in dynamical systems. It happens beyond the boundary crisis, as I already mentioned. It happens in periodic windows, either in period doubling or period adding cascades, or it happens embedded in the Bayesian boundaries when the Bayesian boundaries become fractal. So these are large classes of systems, and therefore we have to expect that these kind of things happen in high dimensional systems. And if we think about, so to say, neuronal networks, so then we have high dimensional systems and we have oscillatory behavior. And now let me show you the role of these chaotic saddles. So in metastability, so for networks of excitable and oscillatory units, so which are described by the Fitzhugh-Nagumo equations, so which is a very oversimplified of excitability, very oversimplified model of excitability. So excitable means that you have an excitatory variable which grows, so to say, suddenly, and then there is an inhibitory variable which grows also, and finally kills the excitation. Now let's have a look at the network of these kind of things. And before doing so, we look at two of them coupled. And this is what's happening. So for certain coupling strengths, you see only low amplitude oscillations. So these two excitable or say oscillatory units, because they are in a regime of oscillations here. So they suppress each other and we have some small amplitude oscillations. But once in a while, when you increase the coupling, something totally different happens. So we see this type of extreme events. So self-generated and terminated events where, so to say, in synchrony, the two oscillators do the same and form such an extreme event. And how it happens, so what's the distribution of those and what's the waiting time between them? This is also something which is exponential, and it's also a Poisson process. So it's again looks like random, even though it's completely deterministic. Now, how does it work? So we look at one in more detail, and then we see our two oscillators, and it looks like these are two friends talking with each other, and one wants to go in the pub and the other doesn't. And so the one which goes to the pub is the red one, so it shoots off and it's pulling the other one, so to say, behind and say, come with me. So, and then they form this kind of event here, so which is this kind of extreme event. So how does it happen is when we look at the mechanism, how this goes is that we have a chaotic motion here with low amplitude, but then, so to say, the transition to this extreme event is also not random. So there is a channel-like structure which pops up here. So where one of the trajectory goes, the other one is pulled behind, and then together they form this event. So this reminds us to the stochastic system. In the stochastic system, we had to go over the lowest hill. Here we have to get into the channel. Therefore, it's rare that you had hit the channel, but it's also recurrent because when you come in here, so you dwell around here and with probability 1 at some point in time, so you will reach the channel and then you develop another extreme event. So it looks like if you play this type of game, so you have to get the real right, so to say, direction to go into this channel and form this extreme event. So this is how it looks like for a network. So where we have exactly this extreme events for a complete network, which is heterogeneous in frequency, so these nodes, but fully connected. And again, we see the type of behavior which we just saw. And this type of behavior happens when an interior crisis, which we just saw, so to say a little earlier, has happened where a period adding and a period doubling cascade come together. And this is a situation which is in neuroscience very often. So I know a lot of neuron models which do that you come with a period doubling cascade from one side, with a period adding cascade from another side, and then this type of behavior can be expected. Now let's get to a video. Wait a second, I have to stop you here. And I want to show you this. Now I'm. So how it happens for the whole network. Let's play this. And so you see, no, you don't see. Yeah. I know. But so now I have even stopped it. So I should take my glasses. This is probably, if I want to see this without glasses, it's dangerous. So, because then I don't see what I'm doing. And I share my screen again. And you should see that. No. So why it's not showing? I have to go to the full screen. Maybe we can share it like this. So, okay. So it has not happened yet, so we have still time. So there is some event, so which we just saw. So where these oscillators here wanted to go off, but it was not strong enough. So not everybody else comes along. So, but there will be, as we see very soon here, so to say, this extreme event where also now sufficiently oscillators together start, so to say, taking off. Now this should happen in the next round. And so here we are. And then they pull everybody else to get to this extreme event. So, okay, so we can stop this here now. And go back to the presentation. Wait, no, I have to stop again and go there and wait, and share it again. Yeah. So now let's get a little bit more involved again. Now we change our topology in the network. So again, we start here now with the square lattice, basically, but now we go to what is called a small network. So where we have the majority, so to say, next neighbor coupling, or a coupling radius, say, around each of the nodes. So this is just a bunch of excitable units or oscillatory units which are coupled. And then we exchange some of the connections with long range connections. Now something completely different is happening. And we will see this again in a video. So we see waves, and now you will see, so to say, there is something happening right here. So watch out. So there, it looks like an extreme event, but it's too small. So we will see that the waves are interrupted by something which is like a flash, and then the waves come back. And then we will speed it up now. So just by going here. So this is all waves, waves, waves. So now we go here. So now you will see there is a transition to something else. So it's coming. So we still see the waves. Now there are no waves any further, but now we see another pattern. So what we see is clusters of oscillatory units coming together, so firing together, and then disappearing again. And these are always different clusters. Sometimes, so they look a little bit the same, but mostly, so this is something else. But now we see some extreme events. That means there is a huge event. So where almost all networks, so to say, is flashing, but then we have a little, so we have a little span of waves. Now we go back to these clusters coming up, and then there will be another extreme event coming here. So we will see another, so to say, flash of now, of activity and so on. This we could see forever, so to say. So if we want to, but we don't want to. So we want to go back to the presentation. So, but this is what we see. So this is what we have seen. And so when we look at the dynamics of this thing, then this is transient. So we have, so in principle, we have three attractors in this system. So these low amplitude oscillations, these traveling waves, and these global oscillations where it's basically, so to say, extreme events all over the place, all the time, so to say, we have those. And so when we now look at the dynamics, once again, so to say, as a still phase, so then we see this kind of relationship. So these are now, so to say, still pictures of the movie. So we have wave structures, we have these little clusters, which are not very nicely seen, but then we have here these extreme events. And so they go, and of course, when we want to analyze the transient dynamics, so what are the times, how long we dwell, what are the waiting times before we go to the next pattern? So then we have to classify these structures. And so there are different types of classification. So we can either do it with Lyapunov exponents, so instantaneous Lyapunov exponents, which measure, so to say, the exponential divergence, so that we have a very different pattern when it's waves, very different pattern when it's these kind of clusters popping up, and also for the extreme events. We can also do another kind of classification. So extreme events, of course, have to cross a threshold here. So this is something we could see. Then we can classify waves and low amplitude oscillations to get a real good statistics. And when we look at the statistics of the whole thing, so then what we see here, that basically the waiting times and the durations, at least for the ones where we have a good statistics, because extreme events, what we have already heard, are rare. So therefore the statistics is horrible. So we cannot really say something. For the waiting times, it's okay. But for durations, of course, since they are short, but there could be also clusters of extreme events. So here, but we see again this random process. So we see that this type of switching, even though it's completely deterministic, so in terms of the dynamics, it appears random. So you see the same as if you would think noise is here in place, but no. So it's purely deterministic, but we still get from one direction to the other. And now we look at this in parameter space. So here are the different attractors. We see sometimes it's bistable, so to say. So this is 100% of all the simulations we have done. And then these are the percentages, how often we end up with which attractor. But in the yellow, and this is the most important part, in the yellow part, this is the parameter here, is the rewiring rate. So that means it tells us how many long-range connections do we have. So at this point, so to say, we don't have any. And here, so to say, when we go further and further, we come to a completely random network. And there is a certain interval. So where, first of all, the convergence to any attractor is very rare. So we have very long transients, and we have a large interval where, so to say, this long hopping process between the different patterns, and this is an irregular switching between those patterns happens. We can also change the heterogeneity in the network, and the same picture, so to say, here we have also two big intervals where this type of pattern switching happens. And the whole thing, yeah. So is for the oscillators, and this is one parameter in the Fitzhugh-Nagumo which determines the frequency. So, and this is the backbone of the whole thing. So this is a chaotic saddle. It's a chaotic set which is unstable and which comprises three different patterns. We are on this chaotic saddle, we are moving between the different space-time patterns without any stimulus from outside. So there is no noise, there's no stimulus, and this is a purely deterministic process which enables the switching. So we can get to the different patterns in this chaotic saddle. And now let us look at the transitions. So we have seen already in two coupled units, there was this channel-like structure through which we have to go, that we develop this kind of extreme event. And we see here the same type of behavior, even for, so to say, for the different transitions from low amplitude to waves, from low amplitude to extreme events. So this is what we had already seen. Here it's not so pronounced that it's really a narrow channel what we see, but here again, when we come from the extreme events into either low amplitude oscillations or wave-like structures, we see this type of behavior, so that we have a certain channel through which we have to go, otherwise there's no transition. And this is, so to say, a cartoon picture how it happens, and the decisive quantity here, and we see that in large now, so is this saddle point here, which is in the middle of this low amplitude oscillation. So this is the saddle, and its manifolds is organizing the dynamics. So if you go on one side of the manifold, you go to the waves from extreme events. If you go on the other side of the saddle point, you go to low amplitude oscillations. So that means the dynamics is completely organized by unstable sets. So the unstable set, which is the saddle point, and the unstable set, which is basically this chaotic saddle, they organize the whole metastable behavior in this type of system. So let's have, for the last couple of minutes, a look at another chaotic saddle and another dynamics. Again, Fitzhugh-Nagumo, yeah. Yes, of course.
How do you get to the extreme events?
So you get to the extreme events through this satellite, this channel-like structure here. So which we have shown already in one of the previous slides. So where you go through this low amplitude oscillations, and then you enter this type of channel, and then you go to the extreme events. It's here the same thing. You can even measure, so to say, with probabilities the size of these holes. And and what I forgot to mention is these holes are not always there. So they are opened when you change parameters. So the location of the stable and unstable manifolds is moving in state space, and they make a room, so to say, for the hole to appear, so where the trajectory can go through. Yeah. Sorry, once again, please. For both, you would see that. Yeah. So let's have a quick look at a homogeneous network. Now we had a heterogeneous. Now we look at the homogeneous, and one cannot even say network because we never considered networks here, but we could. So, but it's identical nodes. And so, but they have a heterogeneous coupling in a way that we have two different delays here. so which connect the two. And then, so to say, we again see a type of metastable behavior, which I would like to explain to you. So because now we have identical oscillators. Identical oscillators are capable of synchronizing completely. So that means you would have, for a low coupling, so to say, with a second delay, so you would have only in-phase oscillations in the synchronization manifold. And for very large coupling strength for with the second delay, you have only out-of-phase oscillations, which are out of the synchronization manifold. So you are jumping off. But in the middle, you have a wonderful metastable dynamics where you switch between so in-phase and out-of-phase oscillations. You have both types. So your trajectory is going somewhere in the, so to say, in the synchronization manifold. Then it hops out, makes an event, so which is out of phase, come back to the synchronization manifold, because here the small amplitude oscillation lies in this. And so this type of dynamics, so here it is once again shown as a time series, just to see red and blue are the different in phase and out of phase, just for you to see that this is also a chaotic dynamics which we see. And we have again this random process of inter-event intervals. So the waiting times, again, a random process, seemingly random process, though everything is completely deterministic. And here's the dynamics. So this is what's happening. This is the mechanism which is now at work. So if we have this low coupling strength for the second delay, so this synchronization manifold is attracting. So everything goes attracted to this, and we are here in mixed mode oscillations even. So this is not even chaotic. So we have mixed mode oscillations, but then there is what is called a bubbling transition. And the bubbling transition has the property so that it leads to certain unstable points, or say regimes, I should say, in the synchronization manifold, which are transversally unstable. So the trajectory finds again the hole to escape. So what it does is, so to say, we have still the synchronization manifold attracting. So that means we have a chaotic attractor here. So in the long-term limit, we would end up here. But so there is a chaotic saddle here, and there is a mechanism, as we said, so that we come close to this unstable regime here. We are ejected, dwell outside, and get back. And if there is a blowout bifurcation coming with another critical transition here for the time delay, so then this thing here becomes transversally unstable. So it's a chaotic saddle, but so this thing becomes a chaotic attractor, but still comes close to the synchronization manifold, so that it looks like a remnant of the stable solution, the synchronized stable solution as we had previously, but it's not stable anymore. So we will not reach, we come only close. And then we go, so to say, again in this out of phase oscillation state here. So it's only close, so to say, when we are here close to these low amplitude oscillations, which are part of the dynamics. So that means we have also a kind of loop here, because this is what is called in-out intermittency. So that means you go close to the synchronization manifold along one orbit. So this is this one. Then you dwell in the synchronization manifold to another orbit, which ejects you again, so to say, to the outside world, out of the synchronization manifold. And this is also a process which you can have for very, very long times. The transients are extremely long, sometimes much longer than your integration time, so you would never see that it ends, basically, if you're not integrating long enough. And so associated with this type of behavior is also that you have even worse basins of attraction than the ones we have seen previously. So we have fractal basins of attraction where you still have these open sets where everything converges, but you have also what is called riddled basins of attractions, where in any arbitrary small neighborhood, and let me show this basin alone so that it is visible. So because this is the basin of attraction of the attractor in the synchronization manifold. And so there in any arbitrarily small neighborhood of the attractor, there is a point of another basin of attraction where you can be kicked out. And this is again, so to say, a situation which leads to this type of metastable dynamics. So this brings me to the end of my talk. And so what I have shown here is that so there are two mechanisms so which can go or can be identified as metastability. One of them is that we have a multi-stable system where different stable regimes coexist, which become, of course, metastable when noise is in place. But then we have also these dynamics, which I just showed, where different saddle regimes, so to say, play a role in mediating the whole metastable dynamics. So which has, and both processes, so to say, the noise and the saddle type behavior, so both share the same properties. So because they are long-lived, they are transient. So then they possess, as we saw, in their surroundings, attracting and repelling tendencies. So this is very important. And this is for both, is this true? So both have this kind of property. But these chaotic saddles in high-dimensional systems are of very high importance, because the higher is the dimension of your system, the larger is the probability that you have chaotic saddles which are embedded in the basin boundaries. That means, so this is a mechanism which in highly multi-stable systems we have always to take into account, but also so even in systems where so we have networks where the single unit would not possess the chaotic saddle, but the network would. And the transitions we have shown also in both cases are very localized in state space. So you have always this type of channels, so through which the trajectory goes. So that means it's not just random where you jump off, but there are certain parts of state space which seem to play a very important role. To identify those, this is of course a challenge. And not only that, so the challenge is of course how we identify these metastable regimes. So there are methods of course available. So we have seen some in the previous talk already, which have been mentioned. There are others also, so how you can identify them, and you can identify the transitions between them. What I was not talking about, but which is of probably equal importance, is timescale separation, particularly in neuroscience. So because what you have is that different processes, the electrical ones are fast and the chemical ones are slow. And this timescale separation plays a very important role probably for the transitions. So we have just recently shown that so that the noise-induced transition of in the Fitzhugh-Nagumo system, depending on the timescale separation, is not going over the saddle point anymore. So because the timescale separation pushes the system away from the saddle point, and that means all these transitions which I have described previously are now again questionable whether this would happen if we increase the timescale separation in our systems, which would be again very important in neuroscience. But this is something we want to tackle in the future. With this, thank you very much.
So this may be a question better asked in the general